Yes, we can start.
What do you want me to read again?
Yeah. Yes, exactly.
Which one? Just abstract?
No, as much as possible.
As much as possible.
Yes, what do you think?
That's a lot of reading.
Yeah, but it's going to help my pronunciation.
What it's going to help your pronunciation is you got to read
Because
it.
I'm listening.
You want me to read again?
Yep.
So you're listening or you're reading?
Listening, and then with the video, I'm going to repeat it again and again and again. Does that make sense for you?
I don't know. Did it help the first time?
Yep. Yep. It is helping me a lot.
You think so, huh?
Yes, I'm the student.
I don't know if I pronunciate everything very good, but
Yeah, it doesn't matter.
it doesn't matter, huh?
Yep.
Okay. Abstract. Background. Contamination of aquatic ecosystems by oil spills associated with petroleum exploitation represents a serious problem of environmental contamination that can affect human health. We developed a spatial model of contamination risk in the Ecuadorian Amazon and evaluated the model using independent data sets on environmental contamination and clinical indicators of human health risk factors. Methods. The spatial risk of contamination for the Napo River Basin was based on the calculation of a friction surface and the accessibility of possible oil contamination. Human health was evaluated using peripheral blood samples from 256 individuals. We used monitoring data on contamination to validate the spatial model of contamination risk and analyze whether the estimated risk explained the incidence of human health risk factors. Results. Our risk model showed a significant association with actual contamination detected in the study area. According to our risk model, around 30% of the territory has some level of contamination. Risk of contamination was associated with an increasing mean incidence and risk factors for human health and resident populations. But elevated contamination risk was not a significant predictor of the incidence of selected health indicators. Only the incidence of inflammation was significantly increased. Conclusions. A large portion of the population in the Napo River Basin has highly vulnerability to contamination from petroleum exploitation. And this contamination risks may be traced in some indicators of health risk. Closer examination of health risk factors is warranted, and our spatial model of contamination risk can inform the design and analysis of such studies, as well as risk mitigation and management. Our approach to building the model of contamination risk could be applied in other catchments where petroleum exploitation is contemplated. Keywords: risk contamination, population vulnerability, oil spills, polycyclic aromatic hydrocarbons, risk model, human health, Ecuadorian Amazon. Introduction. In recent decades, the increase in toxic residues in aquatic ecosystems has attracted increasing attention from researchers and politicians. The impacts of these toxic residues on human health and the consequences by the use and reuse of the water are the main reasons for the renewed attention. Contamination of aquatic ecosystems by anthropogenic activities varied in type and grade of impact. And among these activities, the petroleum exploitation has shown a particularly serious impact in aquatic ecosystems. Notorious disasters such as the Gulf of Mexico in 2010 evidence the environmental damage that can result from the exploration, extraction, and transport of petroleum products. In addition to these large spills, smaller volume oil spills can be alarmingly common and can have significant impacts in oil field areas. The main environmental concern for the risk of contamination from petroleum exploitation is associated with potentially dangerous compounds in oil. Among these compounds, polycyclic aromatic hydrocarbons represent a particularly serious problem of environmental contamination. Petroleum exploration and production contribute in large measure to increased concentrations of PAH. In oil fields, PAH are discharged into rivers as a consequence of spills and leaks and accumulate in the sediments. PAHs can cause ecological and health risks because of their toxic, carcinogenic, and persistent nature. Studies have shown that environmental accumulation of toxic waste from petroleum exploitation can affect human health, and prolonged exposure has been linked to the incidence of development of cancer. Being highly lipophilic and of low solubility in water, PAHs are particularly persistent and toxic organic compounds for living organisms that present a high rate of bioaccumulation in food chains. Petroleum exploration, extraction, transport, and processing involved an inevitable risk of contamination. The quality and the composition of the oil spill, the quantity and the composition of the oil spill, as well as the size of the contamination area, determine the seriousness of the pollution. In this context, the development of models that characterize the spatial distribution of risk of contamination is important to improve the management of aquatic ecosystems. Risk assessment is a systematic process that organizes the identification, description, analysis, and quantification of risk associated with dangerous substances, activities, or events. Therefore, risk is used as a relative indicator rather than an absolute quantitative measure that describes the impact on environmental and human health. Understanding the risk of contamination in which a land and water surface may be exposed is a challenge because of the many variables that influence the movement of contaminants in the environment. It has been common to use simply proximity to known contamination sources to spatially represent the degree of exposure. Such analyses offer the advantages of simplicity, ease of use and interpretation, and rapid preparation, and they have formed the basis of many studies. However, an analysis of risk based purely on distance has its disadvantages. Firstly, the assumption that contamination disperses in a homogeneous manner from the source fails to recognize the characteristics of the contaminant and the medium through which it is dispersing. Secondly, the buffer distances used are often arbitrary and subjective, which may cause gross errors of omission and commission with respect to the distribution of the contamination. More complex models of contamination risk may modify the effective distance by introducing an expected impediment to the movement of contaminants through the environment. be it soil, oceanic currents, or aquatic systems. Incorporation of impediment, more often modeled as its inverse, accessibility, is one alternative that can reduce the arbitrariness of simpler spatial models of contamination risk. The access in the geographic context refers to the effort required for the transfer of an entity from an origin to a certain destination. The approach has been commonly employed in studies of equity access to infrastructure, but little conceptual adjustment is required to apply it to a dispersal of contaminants in the environment. Some studies have modeled the energetic cost or effort of the movement of petroleum contamination from wells, transfer stations, and pipes, and later translated the cost into risk surface. By integrating factors that influence spatial heterogeneity into the dispersal of contaminants, these models successfully link the greater dispersal of petroleum products through the landscape with heightened risk of exposure to contamination. This study aims to model the risk of exposure to petroleum contamination in the Napo River Basin, Ecuador, as a tool to evaluate the vulnerability of human populations. Specifically, we are interested in I, generating a model of spatial risk to contamination by petroleum. 2, validating the model based on independent data set on hydrocarbon contamination in the Napo Basin. And 3, determining the vulnerability of human population to oil contamination in the Napo Basin. We expected that a useful spatial model of oil contamination risks should have skill at predicting actual contamination from independent data. On the other hand, the proposed model is correlated with the probability of contamination. We assume that the localities with the highest risk of hydrocarbon contamination must present high levels of oil toxic compounds that can affect human health. Therefore, our risks model should explain the changes in the health variables. You want me to continue on this?
Yes, please.
Okay. Materials and methods. Study area. This work was undertaken in the mid-basin of the Napo River in Ecuador. This catchment comprises great ecological variation from montane forest to Amazonian forest. The Napo River Basin encompasses the provinces of Napo, Sucumbíos, or Oriana. I don't know how you say those in Spanish.
It is okay.
Okay.
Yes, it is okay.
Most of the territory has a hydrodynamic index, or super humid, and a hot thermal regime. Throughout the 3 provinces, there are a great many water bodies, and the oil wells and pipeline infrastructure of the petroleum industry generally coincide with those water bodies. The Napo River Basin is one of the most important in the Ecuadorian Amazon. It supports a large human population of 416,565 inhabitants. However, the Napo is presumed to have a high level of contamination risk from petroleum exploration and exploitation. The basin has been one of the central areas of petroleum production since exploitation began in Ecuador in 1972, yielding millions of barrels of petroleum. The Napo Basin has the highest density of oil wells in Ecuador, with 886 oil wells distributed over 59,242 square kilometers. Between 1972 and 2009, 740 oil spills were registered. The two biggest spills to date were in 1974 in the Lumbaki Parish, 83,690 tons, and in 2000 in the Hoya de los Sachos Parish, 62,528 tons. Petro Ecuador, blah, blah, blah. Model overview. The spatial risk of contamination by oil was defined in three phases. 1, calculation of the friction surface. 2, analysis of accessibility to petroleum waste. And 3, contamination potential. The friction surface calculated the displacement cost of the petroleum depending on the characteristics of the landscape. The analysis of accessibility established the expected displacement pattern of potential and existing seeps and spills from wells and pipelines based on the friction values. Lastly, we determined the map of contamination risk for the region. Calculation of the friction surface. Calculated a friction surface for contaminants to anticipate the ways in which they might disperse in the areas surrounding a particular spill source. The pattern of dispersal was calculated differently for hydrological networks and terrestrial surfaces. The friction surface in water was conceived as the capacity of contaminants to penetrate the hydrological network. All water courses connected to the contamination sources were selected. Initial friction variable was generated based on the slope map and a map of inundation zones. The displacement costs of contaminants from each cell were conceived as penalty according to the slope. General slopes present a lower excess penalty compared with steeper slopes. Calculated penalties represent the inverse of those used in the method of Agüero and Pujol. The data representing areas subject to inundation were rasterized, assigning the value 1 to the relevant cells. It was assumed that contamination had an elevated degree of access to those units due to their susceptibility to inundation. The surface of the slopes and rasterized inundation data were combined with a condition operator. This operator allowed us to assign the lower values, inundation shape, to those pixels which values in the two layers. Finally, we determined the surface area that would be affected by contamination through an analysis of accessibility. In those cases where a water course may have a level surface around it or land otherwise susceptible to inundation, the maximum distance of penetration would be 1,000 meters. In the case of terrestrial areas, the friction surface was calculated based on the accumulation of flow in the basin as determined from a 30-meter digital elevation model. The accumulation data indicated how water would run overland owing solely to slope. Areas with high values were those that would accumulate more flow, that is, where there was higher probability of flow of water or other liquid. Given that areas upslope of wells, pipes, or potential spills have lower values due to lower probability of inflow, the raster values of flow accumulation were normalized and inverted up to a radius of 1 kilometer around each well, pipe, or spill location. The movement of water, and therefore contaminants, over or through terrain depends on factors such as vegetation cover and the slope and texture of soils. Therefore, to evaluate the surface movement of contaminants, our runoff model incorporated a classification of the land and soil following Razuri. Finally, the soil friction surface was obtained by dividing the inverted flow accumulation layer by the runoff surface. Analysis of accessibility. Accessibility analysis was undertaken for the spread of contamination from each potential source, 886 wells and the system of pipelines across the friction surface for land and water courses. The movement of contaminants depend on the distance to the contamination source and the friction surface from that location. The values for each accessibility layer were normalized between 0 and 100, given that the environment had been conceived from the perspective of friction that limits accessibility. The cells closest to the sources of pollution had the lowest values. To consider the results from the perspective of risk of contamination, the scale was inverted such that the cells closest to the sources had the value of 100, representing the highest accessibility, and the most distant cells had a value of 0. Given that any given cell could be affected by one or more hypothetical sources of contamination, the spatial models of accessibility for the various sources were combined, and each cell was assigned the highest value amongst the set of models. Potential for contamination. To model the pattern of contamination recorded petroleum spill events towards watercourses and lands, we use data on the estimated volume of unrecovered spill and the amount of time that had elapsed since the spill. The volume of spill not recovered was normalized between 0, last volume, and 1, most volume. And the data of the spill was codified as a value between 1, oldest recorded, and 2, most recent. The product of the two variables resulted in a scale where 1 represented a recent spill, where a relatively large proportion of the volume was not recovered. The watercourses that could potentially be contaminated by each spill event were identified and assigned the normalized value previously described. After each implicated watercourse and drainage line was rasterized, all the segments from each spill were superimposed to simulate the accumulation of the contaminants in the drainage network within 100 meters of the spill origin, 1,000 meters. The resulting data were normalized at values between 1 and 2 before being multiplied with the accessibility data generated in the previous step. In the final step, the rasters representing accessibility to contamination directly from wells and pipelines via drainage networks and weighted accessibility from drainage networks, together describing latent risk, and through direct proximity to recorded spills, manifest risk, were summed to derive the final map of the risk contamination by petroleum. The resulting variables was reached from 0 to 1 for each of interpretation. All spatial analyses were implemented in OGIS version 2.6.1. Continue, I'm assuming.
Yes, is that okay? Just the next paragraph,
Okay.
and then we will be done.
How many times you got to listen to that to figure all that out?
Sometimes I just pause in some word that I don't even know that exists, and then I just
That's
tell
kind of
me.
like me. There's some words
Yeah.
there I didn't know existed.
Yeah, exactly. But you know, that's the process of learning. It's like the first time is just listening to you, and the second time is like try to pronounce by myself, and then also sometimes look at the dictionary or just combine with other words and all of those things.
Yeah, some of these technical words I haven't heard before, so.
Yep.
But all right, last one. Model validation. As a form of external model validation, we tested the association between the probability of contamination extracted from our spatial model of contamination risk and detected contamination data from 27 monitoring points and water sources obtained from the blah, blah, blah. These points cover an area of 100 by 60 kilometers with different levels of contamination. This province has been developing an annual program of monitoring of the levels of contamination in the Napo Basin. We used information reported for the concentration of total petroleum hydrocarbons in water and riverine sediments from the years 2012, 2013, and 2014. We evaluated the existence of contamination in 6 samples, 3 sample years, 2012 to 2013, and 2 elements, water and sediment, for each monitoring point. We defined samples as contaminated when the levels of TPH were above the allowed levels of 620 milligrams per kilogram for the agricultural soil and 0.5 milligrams per liter for water. Registro official number 097-A, annexes 2 and 1 respectively. We developed a test for the association between the probability of contamination predicted by our model, risk of contamination, with the probability of real contamination, detected contamination of the water courses. The association was calculated as of Pearson's product moment correlation coefficient. Detected contamination was calculated as DC equals CE over TS, where CE, contamination events, are the times in which samples showed values in excess of the permitted levels, and TS refers to the total samples available from that sample location. The analyses were undertaken with the function of core.test of the stat package in R and